So welcome everyone. Welcome to the day number 5 on 30-day challenge of CSIR net. So today's topic is PN junction diode. Okay. So what is PN and what is P, what is N? We covered in the last lecture that there are two type of semiconductors. One is P type semiconductors, one is N type semiconductor. Now what we can do actually is we can bring them together and we can combine. When we do such kind of thing, the device which we get is known as PN junction. Now, one thing we know is that let me show you a diagram of PN junction diode. It's a very vague diagram or a very rough diagram. So it actually tells you that you have P type of semiconductor on one side and N type of semiconductor on another side. In P type of semiconductor, you have a lot of holes. There are huge number of holes and there are few number of electrons. So holes is in majority and electrons is in minority. While on the other hand, on the N side, there are huge number of electrons. So electrons is given by the red color and holes is given by the blue color. While on the N side, number of holes are very less. So if I give you the picture inside one atom, just one atom. So if I see the atom on P side, if I see the atom on N side, on P side you have trivalent impurities. For example, boron, which only have 3 electrons in their outermost shell. So their fourth, so they have not made any fourth bond because they only had 3 electrons. So boron was neutral, and in the P side you have trivalent impurity. For example, boron, right? And on this side you have, let's say, phosphorus. Okay, both the atoms are neutral. Boron is neutral in its own. Phosphorus is neutral in its own. Boron have made the 3 bonds. Phosphorus has made the 4th bond. Phosphorus has 1 extra electron, which has not bonded with any. And boron has one kind of a hole because it only had 3 electrons. If boron had 4 electrons, then he had also made the 4th bond. But since boron didn't had any 4th electron, there was a missing electron. That's why boron did not make any bond, 4th bond. In general, both the atoms are neutral because atoms in general are neutral. Okay. Now what will happen? The electrons from the N side will see that I can just go and recombine with this electron. This is an absence of electron. So these electrons will see that, okay, there is a vacant space where I can go and sit. So what will happen? Electrons will start diffusing from this side to this side. This electron will come and take this hole. So there will be electron hole recombination will start here. What will happen as a result? Both the atoms were initially neutral, but now this electron went from here to here. So phosphorus became positively charged because phosphorus lost one of its electron. So phosphorus became positively charged. And boron gained 1 extra electron. So boron became negatively charged ion. So as a result, on the N side, you will see there is a positive charges are accumulating, and on the N side you will see there is on the P side you will see there is a negative ions getting made because here we had boron. Boron got the extra electron, so boron became negative ion. Here we had phosphorus, so phosphorus gave his extra electron to him, so phosphorus became positive ion. So on this side, we are getting positive ions. On this side, we are getting negative ions. On N side, we are getting positive ions. And on P side, we are getting negative ions. So when we get these ions, what will happen? So now there will be some electric field which will be generated. Because electric field generates from positive ion to the negative ion. Positive to the negative charge. And these ions are completely immovable. They cannot move. And they are close to the junction. So where they both connected, they are both connected, P and N are connected. Around that junction, there will be ions which cannot move because atoms cannot move inside a material. Electrons can move inside a material, but ions cannot move inside a material. Okay, atoms cannot move inside a material. So they both are immovable. So hence, if they both are immovable, what will happen? So they are immovable and there is a huge electric field which is in this direction from positive to negative. Now, what will happen? Now, if these electrons decides to go again here, because now there are vacancy and these are electrons. So these electrons will, what will these electrons want? These electrons will want, okay, let's go and occupy this hole. But now these electrons cannot go. Can anyone tell me why these electrons now cannot go here and occupy this hole?
Repulsion.
There is a barrier. There is a barrier. There is a repulsion, because you can clearly see these negative ions will actually repel these electrons. So as these electrons will try to come, these negative charge ions will say, no, I'm not allowing you to come. Repel them. So once the electric field is generated, once the ions are generated, electric field will be there. So no more charges will flow between the P and N, and this will be the equilibrium PN junction. Now we are at equilibrium. Okay, so this is what is happening. So let me very quickly recap this. So we had P, we had N. In the P side, we have we want electrons because we have holes. Boron was neutral, but it had only made 3 bonds: 1 bond, 2 bond, 3 bond. It cannot make 4th bond. Why? Because it does not have 4 electrons. It has 3 electrons, so he can make 3 bonds. But the silicon sitting next to the boron wants to make 4th. Silicon says, okay, boron, bring 1 more electron from somewhere so that we can bond together. So boron does not have that kind of electron. Okay. So, but on the other hand, in this side, there was a phosphorus. Phosphorus has already made the 4 bonds, but now it has 5 electrons. Now that 5th electron wants to make an additional bond. So phosphorus is saying to the silicon, please make 1 more bond with me. But silicon is saying, I cannot make 1 more bond. I can only make 4 bonds with you, because silicon has 4 electrons, but phosphorus has 5 electrons. So phosphorus 5th electron wants 1 more bond, but it cannot make 1 more bond. The moment we connected these two, so this electron sees an opportunity. This electron went to boron. So when this electron went to boron, what happened? Phosphorus became positively charged ion because it lost 1 of its electron, and boron became negatively charged ion because it gained 1 of its electron. So now this electron comes and sits in this hole. Now boron has an additional electron, and now boron can make the 4th bond with silicon. Okay. So on the P side, we are getting negative ions. You can clearly see we got negative ions, negative boron ions, and on the N side, we are getting positive phosphorus ions. Now, if more electrons will try to come from one side to another side, what will happen? These ions will give them the repulsion that I cannot allow more electrons to come. So then we are in the equilibrium state. Now our PN junction is in equilibrium state. And in the equilibrium state, what does PN junction has? PN junction has a barrier, or you can say a depletion layer between around the junction. So this line is a junction where P and N connect together. So around this junction, we have one layer which is known as depletion layer. And what is this layer known as? What is the definition of this layer? So the definition of this layer is that this is a layer of immobile. Immobile means that ions which cannot move. Immobile ions near the pH. And due to this immobile ion, we have a huge electric field, or not very huge, but we have an electric field in the depletion, which is stopping more charges to flow. So which is stopping more charges to flow from P to N. Okay. So any doubt in this section? Anyone? The theory of P. Any question? Yeah, please.
So what's the difference between the holes on the P side and the positive on the depletion region?
Very good question. Very good question. So positive. So what is the meaning of hole and what is the meaning of positive charge? Hole mean positive charge ion means that it actually has a positive charge. Means, for example, I had the boron. Boron was completely satisfied. Boron was neutral. Boron had 3 electrons in its valence. It's completely neutral. Okay. Or you can talk about phosphorus. Phosphorus had 5 electrons in its valence and it was completely neutral. If I bring this electron out, then phosphorus became positively charged. So phosphorus is a positive charged ion. It's actually a positively charged. But what about boron? Boron is neutral. Boron is like a neutral person. Boron has no charge. But close to boron, there is a silicon sitting. And silicon has made the 3 bonds like this. And silicon's 4th electron wants to make the bond with boron. So Boron does not have fourth electron to make the bond. So there is a vacancy of electron which is there, means there is absence of bond. So absence of bond could be seen as hole. However, there is no net charge. Boron is neutral, silicon is neutral, but both of them are unable to make the bond with each other because the extra electrons which boron need, he does not have. Okay, so absence of bond is actually hole. Okay, electron missing, electron is not missing. Electron, it means he does not have extra electron. However, his own electron is not missing. Boron had three. Boron is born with 3 electrons. So none of his electrons are missing. But as he grew up, he saw that if I would have one more electron somehow, I can make bond with him. So that desire to have one more electron, which he does not have, is whole. But what about phosphorus? Phosphorus was born with 5 electrons. Now one of his electron is missing. So he has a positive charge because out of his 5 electrons, 1 electron went out. So that is a difference between the positively charged phosphorus and boron, which is neutral but have desire to have the extra. Okay, you understand my concept?
Yes, sir. Understood.
Excuse me, sir.
Yeah, please.
Sir.
Yeah, please.
So holes of different atoms acts differently?
Yeah, definitely. 110%. Because each atom disturbs or forms the bands differently. EK diagram for each atom is different. So
Okay.
effective mass of each hole is different.
Okay, thank you, sir.
Yeah. Yeah. Any other question? Everyone clear with this much theory? Can we move forward? All clear, everyone? Any confusion?
Yes, sir.
Okay, great. Now there is a symbol of p-n junction diode, we all know. So p side is given by triangle and n side is given by this. So can anyone tell me what is the basis of this symbol? Why we made this symbol only, not any other? We are studying p-n junction from like we are in BSc MSc. We should know that. Why is this? Anyone? Any guess? It shows the direction of current, which is true. Which is true. So p-n diode is actually something in which the current can only flow in one direction. You cannot have current flow in both directions. In resistor, what happens? You apply battery like this, your current will flow like this. If you apply battery reverse, your current will flow in opposite direction. But in p-n junction diode, it cannot happen. In p-n junction diode, current only flows in one direction, and that's all. Then we cannot have like this. Why I'm saying that it is only that? Because if I want positive charge to flow from N to P, I cannot do that. I cannot do that. My N has limited number of positive ions. For a moment, assume that holes is something which is positive. Just assumption. I'm not saying it is actually something positive. But let's assume that hole is something positive. And I want that positive charge should go from here. So I apply my battery. So it is positive terminal and it is negative terminal. So I want that my positive charges go from N to P. N has a very limited number of positive charges. How can little bit 3-4 positive ions will go on this, holes will go on that side, but not more than that. So we cannot have much current, positive current going from here. But if I want the reverse, I say, okay, I want my positive charges to go from this side to this side. That I can do a lot because on this side, I have a lot of positive charges, which we can say that I have many holes. So I can make that hole going from this side to this side. Okay. So I can flow my positive current from this side to this side, but not from this side to this side because my N does not contain enough holes. Or you can think, or you can understand this in reverse direction. Let's say I want my negative charge to go from this side to this side. So I can make that happen because N has a lot of negative charges. My negative charge can go from N to P. But if I want the reverse, I want my negative charge should go from P to N. That cannot happen much because P has a very limited number of negative charges, very minimum number of electrons. So little bit current can go in this direction, but mostly current will not move. Okay, so that is why your current can only flow in one direction in p-n junction. As a result, the symbol is there. So symbol says that if you come like this, then you can go. But if you come from here, then you have a barrier. Barrier which will stop. So you have a wall which will not allow the current. But if you come from here, then you have an arrow which will be actually showing that current can go in this direction. Is it clear, everyone, about why this symbol?
Yes, sir.
Okay, great. Now you know whenever there is an electric field, there is a potential. Electric field basically means potential. What is the connection between electric field and potential? The connection is that, so now we have, this is P, this is N, and on P side we have positive ions, and on N side, P side, we have negative. Now if this positive charge from here, let's say holes from here, wants to grow from here to here, they cannot, because there is a solid electric field which is stopping it. There is a solid electric field which is stopping it. So if there is a solid electric field, it means there is a potential, because whenever there is an electric field, there is a potential. Electric field basically represents force, and potential basically represents work. So whenever there is a force, there is a work done, as long as you want to displace in the direction or opposite to the direction of force. Right? If you're not moving perpendicular to the force, then work done is zero. But if this is a force and you want to move either in this direction or opposite to this direction, you will have work. So electric field represents force and potential represents work. So as long as you have electric field, you have potential. Okay. So there is a potential barrier. You need to provide this much potential to your charges so that they can actually move from one side to other. So if you want, no, I still want my holes to go from this side to this side. They are not going by themselves because the barrier is stopping them. Electric field is stopping them. But I want that, no, I still want my charges to go, my majority charge carriers to go from one side to other. Then I have to apply some voltage or some potential. And that potential that I have to apply to make sure that my majority charge carriers move from one side to other is known as the potential barrier of that diode. Okay. So if I apply, let's say, so in case of, let's say, simple cases, for silicon, let's say it is 0.7 volt. So in silicon, if you want that your majority charge carriers goes from one place to another against the potential barrier, you have to apply at least the battery of 0.7 volt so that your holes can move from one side to other, or electrons can move from one side to other. Your majority charge carriers can move against the potential barrier or against the electric field inside the depletion. Okay. So I hope I am clear with that. What happens in the depletion region when the current passes through it? Yeah, I have biasing. So basically you're asking biasing. I will explain that. Okay. So now what about the width of depletion layer? So there is one very common formula which is being used in some of the problems, and that formula is, let's say there will be some width. Will that width be same on both sides? The width of depletion layer along N side and width of depletion layer along P side, will that be same or not? And the answer is no, they will not be same. It actually depends upon the doping. How much doping you have done. Let's say on N side, if I have done a lot of doping. So doping on N side is ND. So I have done the doping on N side ND, which means donor doping. Donor means pentavalent, which have an extra electrons. So I have done donor doping on N side and acceptor doping on P side. Acceptor means people who want the electron, trivalent impurities. So doping on N side is ND, doping on P side is Na. More the doping you do, let's say I do the very, very large doping on ND, then the depletion width on N side is very small. If the doping on N side is more, then the depletion width on N side is less. Okay. But however, if the doping on P side is more, let's say Na is very more, then ND will also be very more. So the dependence of your width depends upon the doping on other side. If I am on N side, I am the width on N side. And if doping in N side is more, then my width will be less. But if the doping on P side is more, my width will be more. And the formula says that width along N side multiplied by doping along N side equals to width along P side into doping along P side. And you can clearly see that Xn is directly proportional to Na but xn, this will go here. Xn is inversely proportional to n. So this is a very important formula that you might require for solving the problems. I can give you the total width, okay, and I can ask you, and I can even give you the doping ratios, and I can ask you what will be the ratio of the depletion width, and you can find using this formula. Okay, so this is the formulas about the diodes in equilibrium without any bias. Any question anyone have, please ask.
Hello, sir.
Yeah.
Sir, in the previous slides, what were the ND and NA were?
ND was the doping in N side. ND was doping concentration in N side, in N type semiconductor, and Na was doping concentration in P type semiconductor. Okay.
Yes, thank you, sir.
Okay. Okay, everyone clear till here? I can move forward if you allow me to. Okay, everyone
Yes,
understood?
sir.
Yes,
Yes,
sir.
sir.
Sure, thank you. Okay, let's move on. Now, biasing of diodes. So, very simple topic. Biasing basically means applying the battery. So, if you apply the battery, now you are disturbing the system. Your diode was at equilibrium, now you are disturbing it. And you are applying the battery. Okay, so it's a very simple process. First of all, understand that you can actually replace your PN junction diode with an equivalent circuit. Okay, I will come to that point at a later stage. I will come to this. Let's first understand what is forward biasing and what is reverse biasing. Okay, then I will explain you that how you can replace your diode with the equivalent circuit. Okay, let's come to the forward biasing. The very basic rule of forward biasing is that connect N to negative and connect P to positive. So if you are applying the battery, connect your N side to the negative side and connect your P side to the positive side. Now you can clearly see that what is going on. So now you have the electrons, a lot of electrons in N side. Let's talk about any one of them, either electron or holes. So I prefer to talk about electrons. So let's say there are huge number of electrons. No, it's actually true. Okay, it's actually true that we have a huge number of electrons on the N side. If we have that, now we have two factors. One is that depletion region, or one you can say is that potential barrier. So this potential barrier does not want this electron to come. If these electrons will try to come here, these negative charges will repel. But now we have additional outside help, and this is our outside help. Our battery is our outside. So this negative terminal of the battery will push the electrons in this direction. And so my battery and my depletion layer both are working in opposite directions. As a result, what will happen? All these charges will getting squished. Means these electrons will start moving in this direction if the effect of my battery is more than the effect of depletion layer. Let's say depletion layer voltage is 0.7 volt. And I am applying the battery of 2 volt. It means I have the enough voltage. So what I can do actually is my electrons will pass through this depletion layer and they will go and move to the other direction. So I will have the current in the circuit. I will start having the current in the circuit. So since the depletion layer and battery is working in opposite directions, I can say that if I am applying the forward biasing, my width of depletion layer will keep on reducing. It will keep on reducing. As more and more battery I keep on applying, my width of depletion layer keeps on getting smaller and smaller. Okay. So these are the two concepts you have to understand, that in forward biasing, your external battery works opposite to the depletion layer. And as a result, it makes the depletion layer smaller. And in this case, if your battery is larger than the potential barrier, then your majority charge carriers will start flowing. Okay, so your majority charge carriers will start. And if your battery is less than the potential barrier, then sorry to say, your majority charge carriers cannot flow. Okay, so once your battery becomes more than potential barrier, your charges starts to flow. Which charges? Majority charges, and then your current will increase exponentially. then you will have a huge amount of currents in your circuit. And that is what is represented by IV diagram. IV diagram or VI characteristics of any device is very important in electronics. Whenever someone gives you any device, you have to first ask that what is their VI characteristics. And the entire research of physics is finding the VI characteristics of different bodies. So VI characteristics basically says that until unless you're up to some certain voltage, there is no current because your battery is less than the potential. But once you start overcoming that potential barrier, more and more electrons start moving, and ultimately you have an exponential curve. Means now your current is increasing exponentially. So this is known as the forward biasing characteristics. Up to some level, you don't have any current or almost zero current. And after a certain level, you have a peak of current or exponentially increasing current. Okay. The point where you see that you start getting this kind of line where your current actually starts increasing exponentially, that point is known as the knee voltage of your circuit. And usually this depends upon your material. Is it silicon, germanium, what is it? Okay. So any doubt in forward biasing? I hope there will be some. You can ask me any questions in forward biasing. Yeah.
Sir, knee voltage, can you please explain?
So the moment the current, so once you draw the graph, an actual practical graph, you will see there is so it does not happen like this. So it is an ideal case. This is your ideal case. What is an ideal case? That up to a fixed value, you have no current, and then your current suddenly start increasing. This is an ideal case. Usually what happens is that your current slowly your current slowly starts increasing. So up to this region, you cannot say that you are actually in exponential region. After a certain point, you will see, okay, your exponential growth has started. So the moment your exponential growth started, that point is known as knee voltage. Okay.
Okay, sir. Thank you.
Sir, I have a question. How the width gets smaller when the doping concentration is high? Okay. So I will talk about this. I will take this question in the end of the class. I will explain. Okay. I will explain it to you. Okay. Yeah. Any other doubt? Will the semiconductor heat if the voltage is increasing? Obviously, if the current is increasing, then semiconductors have their resistance, and as a result, it will heat up. Any device which have a current through it have heating up because it has its resistance. Okay. Now let's come to the reverse bias. Before the knee voltage is the current due to minority charge carries. So how can minority charge carriers? Yeah. So we have to apply the negative voltage for that. So let's say current because of minority charge in forward bias. So now N has holes as well. N has holes as well, and P has minority electrons, some electrons. Now, even if these electrons want to go in this direction, even if they want, this positive battery will not let them go because this positive battery will attract these electrons towards it. So this positive battery cannot allow the electrons to move in this direction. So when you are in forward biasing, reverse current cannot happen. Okay, current will be positive. This will never happen that your positive battery is like this. So current start coming in opposite direction because of minority charge. No, because the minority electrons in this cannot move in this direction because of this positive battery which is attracted. So in forward biasing, there is no reverse current. Okay. They are because of the majority charge. This current, the entire current before the knee voltage, even this small current is also because of the forward current, but they are small. For example, you need a potential. There is a potential barrier of 0.7 volt. So in order to make sure that your electron goes from here to here, you need 0.7 volt. But let's say you are at 0.5. I agree that not many electrons will go here, but some will still go. No? Some will still manage to go. Some will, because they also have their own energy. Because of the temperature, they are also moving. So let's say they were already moving, and they had some sort of, already they have some energy, and additionally I gave one push. It was not enough push, still I gave some push. Some of the electrons will still go from this side to this side. Because of that, this small current is coming. And once I'm beyond 0.7 volt, then almost every electron can move forward, and more voltage I will keep on increasing. More and more electrons will keep on going from this side to this side. Okay. So this entire current is positive current. There is no reverse current as such. Okay. Fine. Okay. Let's come to the reverse biasing. And what does reverse biasing has to say? Reverse biasing rule is very simple. Connect N to positive and P to negative. So now we are actually helping the potential. So what is happening? So we have the electrons. So if electrons try to go from here to here, the potential barrier repels them. And now even if the electrons try to go from here to here, this positive of the battery will attract it. Means this positive of the battery will not allow electrons to go from one side. So now our battery is helping the potential. So now the flow of majority charge carriers will even be more and more impossible. Because now our positive charge carriers cannot, our majority charge carriers cannot flow, because initially already they had the potential barrier. And now my battery is also adding up to that potential barrier. So there is no flow of majority charge carriers. As a result, your depletion layer keeps on getting bigger and bigger and bigger. Okay. So this is what happens in reverse bias. But there is one more thing that is happening, and that is the flow of minority. I agree that majority charge carriers cannot flow. Electrons cannot go from here to here. But there are some electrons here as well, which are minority charge carriers. They can certainly go from here. Why? Because now this negative of the battery will repel these electrons and say that go on this side. Once the electron go from here to here, your current is actually from N to P. Why? Because current is opposite to the direction of flow of electrons. So if electrons are actually going from here to here, so now which charges are flowing? Minority charge carriers are flowing. So minority charge carriers are flowing, so current is in opposite direction. Okay. So your battery, if you apply a battery, then current should come from positive side. But no, it is not happening. Current is not flowing like this. Current is flowing like this. So it is a reverse current. It's a negative current. So you applied the battery, positive here, negative here, but your current is not from positive to negative. Your current is from negative to positive. So it's a kind of a reverse current you are seeing in your circuit because of the flow of the minority charge carriers. Okay. But the problem is that there are not many minority charge carriers. Minority charge carriers are very small. So let's say you only have 10 electrons or 10% minority charge. Only 10% of the current or a very small portion of current can come. Not a large currents can come because minority charge carriers are smaller in number. That is why current, because of minority charge carriers, is also smaller in number. So this is how you see your reverse biasing. In reverse biasing, you are applying a negative voltage now. If forward biasing is positive, then reverse biasing is negative voltage because you switched the battery. And because of that, the current is also coming to be negative. If initially the current was like this, then now the current is like this. So now your current is also negative. But you can clearly see, so ignore this part. I will explain this part. But only to here, you can clearly see there is a very small current. And this is a constant current. Small current, though I understand that this is a small current because there are not many minority charge. But why this is a constant current? Can anyone explain that why the current is constant here? Small I understand, but why is constant? Why it's a constant?
Because the number of minority charges are limited, so no matter how many voltage we give, the current will remain the same.
Yeah. So I had the 10 electrons, only 10 minority electrons, and I applied the battery. So initially 2 electrons went there, some current came, then 4, 6, 8, 10. Once all the 10 electrons are there, I got my current. And even if I increase the battery even more, no current is going to change because I only had 10 electrons. All the electrons are on the other side. They are moving on the other side. how much more current I can give you. All the electrons, all my minority charge carriers are under action. They all are going from one side to other. If even if you increase voltage even more, I don't have any additional minority charge carriers to move from one side to another. So current will become constant after a while, and then it will remain constant. Okay, and
I
that is
have a doubt.
yeah, please.
I have a doubt here. See, if I increase the potential, this means the traction force will be more. If the
Which force?
traction force between the minority charges that is causing the current, right?
Yeah. So minority will try to go more like
It will move faster, right?
they will move. No.
Why not? If the traction is more, and increasing the after increasing the potential, why won't they move faster?
Yeah. At the moment, I also thought, but drift velocity of semiconductors is nearly independent of voltage up to a certain. So drift velocity is even if so attraction is more, but in this moment, what will happen that in order to achieve that, your collisions with the atoms will also start to increase. So as a result, the drift, if you carefully calculate the drift velocity for semiconductors, if you take the course and if you find that, then you will realize that drift velocity for semiconductors comes out to be very nearly independent of potential up to a certain potential. And you need to have very high potential to change the drift velocity. And actually at that drift velocity, you will achieve the Zener breakdown before actually achieving that your drift velocity is changing. So drift velocity remains constant because the collisions also starts on increasing as you increase the potential. Probability to collide also increases.
Sir?
Yeah.
Sir, can you tell once again, like, what about the width of the depletion region in reverse bias? What will happen?
In reverse bias, the width of the depletion layer will keep on increasing as you apply the voltage more.
So, sir, the electric field also will increase?
Yes, will increase. Will increase.
Excuse me, sir. I had a doubt. Like in forward bias, it can stop up to 0.7 volt, right? Like until 0.7, the volt, the current will be very small, and after crossing that barrier, the current keeps flowing. So compared to these 0.5, how much that reverse voltage can it block? Like, will it be 10 volt, 20 volt? How much volt can it block? Like maximum, how much
It is
has
not
it blocked?
blocking. Barrier is not blocking reverse. Reverse to helping the barrier. No? So if this is a barrier and if I am so reverse means that I am so blocking means I'm trying to go against the barrier. But reverse is actually trying to help the barrier. So if initially the barrier is this much, I apply the reverse, barrier will even get bigger.
Okay, basically my question is how big is V2 compared to VP magnitude?
How much? How much?
Yes, sir. Like in this graph, this V2 is there, right, sir? V2.
It's VZ. It's VZ.
Yeah, VZ. Yes, sir. This VZ. How big is VZ in magnitude compared to VB? Like how much big it is?
Okay, so this Zener diode voltage. So Zener diode voltage. So it basically. So this is a Zener diode voltage. I'm coming to that why it is coming, but
Okay,
it is not. So you are okay. Let's first understand what is Zener diode voltage, and then I will, in my explanation itself, I will give you the answer. Okay.
Okay.
So let's understand that once the current was constant, then why suddenly the current increased so much? Current increased so much that you can see the so much current without even increase in any voltage. It's so huge current in increase. Why that happened? So that happened because you had an atoms. So we had an atoms, and inside that atoms, now I am applying the electric field, reverse electric field. I am keep on applying the reverse electric field. All my electrons are already there. I have got the saturation current. More I am applying the reverse voltage, it is not helping at all in increasing the current because you are increasing the reverse voltage, but the current you can clearly see is saturated. It has a saturation. So by increasing the reverse voltage, there is no help as at all to increase the current. But what this electric field is doing, what this negative voltage is doing actually is more voltage means more electric. And what is happening there is that inside atoms, what will happen? the electrons will experience this force. And as a result, ultimately the force will become so high that atoms will break, means the valence electron will come out of the atom. And this can happen easily. You know that if you want to remove the electron from any atom, there are 3 or 4 ways. One, you heat it. Second, you drop some light on it. You illuminate it with some light. Or you apply the electric field. And this is exactly what I'm doing here. I'm applying the electric field. So more and more and more electric field I keep on applying in this direction, in negative direction. Inside my atoms, electron will start experiencing force, and ultimately what will happen? These atoms will break. So electrons will come out. And you know what happens when atoms break? What happens when bond break? So bonds will break. What happens when bond break? We get a lot of minority charge. You know that. We studied in the last lecture that whenever the bond breaks, we get a lot of minority charge carriers. And suddenly at this voltage, huge amount of minority charge carriers are produced. As a result, what you wanted? You wanted minority charge carriers, because in reverse biasing, only minority charge carriers can flow. So once I produced a lot of minority charge carriers, now my minority charge carriers can flow from one side to the other, and I will get a very large reverse current. So very basic 3 things happened. I kept on applying my electric field. As a result, bond breaks. If the bond breaks, huge amount of minority charge carriers are produced. And in reverse biasing, only minority charge carriers can flow. So since I have a huge amount of minority charge carriers, I have a huge amount of minority charge carriers flowing. As a result, I have a huge amount of reverse current. And this reverse current you can easily see here. Okay. And that is why the Zener voltage is coming. This peak is coming. And to determine the value of this VZ, it depends upon 2-3 things. Number one, it is roughly, it can be from 10 volt, even lesser than that. In your chip circuits, this Zener volt is even millivolts. This Zener voltage is actually can be engineered to any value, because this is in entirely our hand. This is not a materials, almost material property, but not entirely materials property, because it is a voltage stabilizer. In your voltage stabilizer, you can use your voltage stabilizer at 220 volt. You can use your voltage stabilizer at 110 volt. In America, they are using at some other voltage. In India, they are using at some other voltage.
Sir,
In
does
yeah.
stabilizer has diodes inside?
Yeah, we have
Oh,
diodes. Yeah, we have diodes.
in the stabilizer.
Yeah, inside stabilizer, we have a Zener diode.
Okay, sir. Thank you.
Yeah. So you can clearly see we can give as much current to the Zener diode, Zener voltage, and you can see your voltage is not changing. Current is changing. Y-axis is changing. Current is changing. But you can clearly see that your voltage is not changing. So that is what our stabilizer do. Even if the large current comes from behind, your voltage is not going to change. That is the whole purpose of the. So Zener, what does Zener diode do? If an extra current comes, let's say our device needs 2 ampere current, and let's say suddenly from behind, from the back end, 5 ampere current came. So what will Zener diode do? Zener diode will make sure that current through this is still 2 ampere, and rest of the current he will take through himself. 3 ampere current he will take through himself. And even if he takes the 3 ampere through himself, his voltage is not going to change, because current can change, but voltage will not change. So Zener diode will remain at the same voltage, and whatever extra current is coming, Zener diode will absorb that, and current through the load or current through the device will remain same. That is how Zener diode works. Okay. Any question till this point? You are free to ask. Why this bond? Why this is coming? Everyone understood? Everyone got an idea why the Zener breakdown is happening? Because next topic is, I'm going to, in this next slide, I'm going to explain that how to solve the problems of Zener diode. Okay, so if any doubt is there, let me know. Okay. Then we need a very important formula, which is current through diode. So current through diode formula is I equals to I saturation, some constant current. Okay. So IS is some constant current. current. So this is a saturation current in reverse biasing. You can clearly see this saturation current. So the magnitude of that. So let's say this saturation current is minus 2 microampere. So IS will be 2. Magnitude of that. IS will be 2. Okay. Good. So then what will happen? Ananya, we can increase the voltage through Z. It's not a restriction that we cannot increase the voltage. If we keep on increasing the current, ultimately there will be a point when the voltage through the Zener diode will actually change. But there is a huge range of that. Means within 10 ampere of current, voltage will not change. And that much is fine with us. That within this 10 ampere, we can use our Zener diode. So every Zener diode will come with the rating that you can give him a maximum current of this. You cannot give it more than this current. Otherwise, what will happen? Its own voltage will change. So we can change, but there is a limit to that. That within this limit, it will not change.
Excuse me, sir. Is there any specific formula which determines visit?
Coming to that.
Okay, sir.
Okay. So current through the diode is IS. IS is this saturation current whose value is most probably given to you. IS is basically the current flowing in the diode when it is reverse biased. It's known as a saturation current. Into exponential E. E is a charge on electron. VD. VD is the voltage you applied across the diode in forward biasing. Applied across the diode in forward biasing. Divided by eta KT. K is the Boltzmann constant. T is the temperature minus 1. So your eta is 1 for germanium and eta is 2 for silicon. And if it is not mentioned that is it silicon or germanium, always take eta 1. Okay. If it is not mentioned, then always take eta 1. Okay. So that is what your thing is. And this will be your formula through the diode. I already explained Zener breakdown. One more breakdown which I want to explain is avalanche.
Excuse me, sir. Like a doubt about the formula. This applicable for both forward and reverse biasing.
For reverse, I already gave you the current. It is IS.
Okay, so
even if you increase the voltage, IS remains IS. So
okay,
it is not available for Zener. This is up to the normal diode function. This formula is not going to the Zener side.
Okay, sir. So only right side.
This formula is for these characteristics. That no Zener for these characteristics. So for reverse, I already told you the current is IS. So this voltage we will apply as forward.
Yes, sir. So this constant value we can see, right, sir? This in left side is this IS?
Yeah, this is IS. This is IS.
Okay, sir. Okay, sir. Yes. Thank you, sir.
Okay. Okay. Now, one more breakdown which I quickly want to explain, which is avalanche breakdown. Then I will come to the point where I will start explaining you that how to solve it. Okay. So avalanche breakdown. So I already got Zener breakdown. So in Zener breakdown, what happened? My atoms got so excited that electrons went out. So I have now positive ions. When the electron come out of an atom, I get a positive. Now, if I even keep on increasing reverse voltage even more, then what will happen? These ions will start moving because now they are inside an electric field and they start moving. And what will happen if they start moving? They will start and colliding with each other. Means other atoms which are still neutral. So these ions will go and hit those atoms. As a result, the electrons from those atoms will also come out. So if I even keep on increasing voltage even more, once I got a Zener voltage, again, still I'm making sure that I'm keep on increasing the voltage in negative side. Ultimately, a point will come that my ions will start moving around my electrons will start moving around, and ultimately they will go and hit the other atoms. And as a result, what happens? You can actually see that your more and more electrons will start coming up, and there will be another level of breakdown which will be avalanche. Let's ignore that part. Not very important. We have another breakdown, avalanche breakdown. In last many years, no question from here. Just for the fulfillment purpose, I have written. Now comes the very important, which I really want to emphasize on, and I really want to comment on very fast on it. That is that how to solve the Zener diode problems. Let's say
sorry, sir. Like just before going this, like just one minute, sir. Like Like what is the main difference between avalanche and Zener breakdown, sir? Like what is the main difference between these two?
Basically voltage. It is a primary breakdown. So that happens because initially you have made an ions. Now that is a secondary effect. In what will happen when the electrons come out, they also start having an effect. Electrons start moving and they start going and hitting the other atoms. As a result, secondary emission happens. In an atomic physics, we learn about the secondary emission. So one electron goes and hit the electron of other atoms, and or it is actually not hitting, it is actually supplying its own energy to other atoms. As a result, its own other atoms electrons will also start coming.
Okay, sir.
Okay.
Thank you, sir. Yes,
Okay.
madam, sir. Thank
Okay. Any Zener diode question comes in the same way. There is not even a single Zener diode question which will be different from this question. There is a same tactics for every Zener diode question. Okay, one will be, even in TIFR, anywhere in JEE Main, JEE Advanced, BSc, TIFR, anywhere, Zener diode circuit is same, and that circuit is, you will have few things. Number one, you will have input voltage. Now, this input voltage can be fixed, or this input voltage can even be different. That depends. It will be either 5 volt, or they can say it can be anywhere between 5 to 30 volt. So anything can happen. So there will be some input voltage. There will be some series resistor. So some series resistor will be. There will be Zener diode, which is reverse biased. You can actually see the negative side is connected to the positive side, and negative is connected to positive. Okay, positive to negative, negative to. So this plus is connected to N, and this negative is connected to P. So this is reverse biased. So Zener diode always works in reverse bias. And in the end, you will have the load. Load can be anything. So in circuits, we draw a load resistor, but in actual reality, load can be air conditioner, it can be fan, it can be laptop, it can be mobile charging, anything. So it is our load. So we will be given series resistor, we will be given load resistor, we will be given input, and we will be given Zener diode. Okay. So now few things which can be written, can be given is that what is the voltage across this Zener diode? Let's say that Z voltage is Vz. Okay, and this is input voltage. Okay, so voltage across Zener diode can be given to you, and in most of the cases it will be given to you. Now, can you tell me, if the voltage across Zener diode is Vz, then what is the voltage across resistor, which is load voltage? If the voltage across Zener is Vz, then what is the voltage across load?
VZ.
Same, sir.
Vz, because this thing and this thing, both of these are in parallel, and in parallel voltage remains same. So if the voltage across Zener diode is Vz, then the voltage across load resistor is also Vz. It means your VL is equals to Vz. This is the trick number one. Your load will always be connected to the Zener diode, and whatever is your voltage across Zener, that will be the voltage across load. Now, what will be your current from the input battery? So let's say your current from input battery is coming as I. So this current will flow from series resistor, and then this current will split into two parts. One will be Zener current and one will be load current. How do we calculate the load current? It's very simple. The voltage across load we already know. So how do we find the current through load? Current is always given by V by R, and voltage through load we have already calculated, which is Vz divided by RL, which is the load resistance. Okay, so two things you have figured out: voltage across the load, and second thing is current through the load. Okay, if you know the load resistance. Okay, now can anyone tell me what will be the voltage across this the resistor? By looking at the diagram, what will be the voltage across this series?
V input minus VZ.
V input minus Vz, because total voltage you had was V input. Out of that voltage, Vz goes to Zener, then whatever is left goes to there. So let's say this is 12 volt and your Zener voltage is 10 volt. Then the voltage across this is 12 minus 10, which is 2 volt. Because out of 12, 10 goes to Zener and 2 remaining goes to RS. So the voltage across series resistor can be calculated as V input minus Vz. Then what will be the current through input resistor? Current is always given by V by R. Vs you have already calculated, which is Vn minus Vz, and Rs is the series resistor. So you also know the current through series resistor. So I know I have also calculated IL. Then what will be the IZ? IZ is also very simple. So IZ will be total current minus load, because total current was I, and that went to IZ and IL. So this IZ current will be equals to total current minus load current. Okay. So let's do this thing in a problem so that you can actually understand what I'm talking about. This is one of the previous year question. So in this question, very simple problem. Input voltage is given to you 40 and zener voltage is 20 volt. So if zener voltage is 20 volt, what is this load voltage? This is also 20 volt, because this thing and this thing are in parallel. Out of 40 volt, 20 volt goes here. So what will be the voltage here? This will also be 20 because this is 40 minus 20, which is 20. So total 40 volt was input. Out of that, 20 goes to zener. So remaining 20 goes to this series. Okay. So based on this information, can we find IL? Very simple. VL by RL. VL we already know. What is VL? 20. What is RL? 20 kilo ohm. So this will be equals to 1 milliampere. Can I find this IS? Yes. Very simple. What was the voltage across is 20. And what is its resistance? 10. So what will be this? 2 milliampere. So total 2 milliampere current is coming up. 1 milliampere current goes here. Then you can all tell me what will be the current through zener. That will also be 1. So your answer for this question is 1 milliampere. So you understand that how to solve the problem. I will be discussing much more difficult questions as well. But do you understand this one, everyone?
Yes, sir.
Yes, sir.
Sir, repeat again,
Yes, sir.
sir. You are going fast.
Yeah, I can go again. It's very simple. So let's go a little bit again. So your total voltage is 40 volt. Okay. So your zener voltage is 20 volt. So if voltage across this is 20, then voltage across this is also 20, because both of them are in parallel. So now your total voltage was 40 volt. Out of 40, your 20 goes here. So where else is your 20 now? So 20 is here. So out of 40, 20 goes to zener and 20 goes to series resistance. So voltage across series resistance is 20 volt. Now I can find the load voltage. What is the voltage across this load? So IL can be found as VL by R. What is VL? VL is 20. What is this resistance? This resistance is 20 kilo ohm. So 20 by 21 kilo will become, if it goes up, it will become milliampere. Okay. So the current through the load is 1 milliampere. Now let's find the current through this series resistor. Current through this series resistor is again voltage 20 divided by resistor 10 kilo. So this will be 2 milliampere. So 2 milliampere current was coming up. Out of 2, 1 goes here. Then how much will go here? It will be 1. So 2 comes, it splits into 2 parts, 1 milliampere here, 1 milliampere here. So basically they ask that what is a zener current? So this zener current is nothing but 1 milliampere. Fine, everyone? So
Yes, sir.
Okay. Okay, great. Okay. So if it is clear, let me explain you some of the basic rules more before I jump into the problems. Very simple rule is, this is your diode. Okay. This is your diode. Let's forward bias it. If I forward bias it, I will apply positive here and negative. If it is not ideal, let's say it is not ideal, I have given its potential barrier as, let's say, 0.7 volt. This is not an ideal diode. Its potential barrier is 0.7 volt. Then replace this diode with a battery. So if this is P, this is N, then replace this diode with the battery. And this battery will have the voltage of 0.7 volt. So in a circuit, whenever you see that your diode is being forward biased, and if it is not diode and this potential barrier is given to you, or it is mentioned that it is silicon, then what you can do is you can replace your diode with the battery of 0.7. Remember, you have to connect your P side, means you have to replace your P side with positive and N side with. So this thing will become this. But let's say it is
So
ideal.
can we do it with any other value?
Yeah, yeah,
Like
whatever value is given. Whatever
1.1.
yeah, whatever is
Okay.
value is given in question, that you can go with. Okay. You have to go with whatever value is given in question, not only 0.7. Now, if it is ideal, I said this is an ideal diode. In that case, simply replace your diode with a wire. And in wire, always remember one thing: if it is not written ideal, and if it is written that it's a non-ideal, then take 0.7. It's a safe. Okay. If value is not given and material is given to you, silicon, germanium, take 0.7. It will work. Okay. Good. Then for ideal diode, what will happen? Replace the diode with the wire. In wire, one thing is very important. If your voltage here is V1, then your voltage here is also V1. Voltage at all the points on the wire is same. You always have to remember this, or always have to think this concept, that in a wire, voltage at all the points is same. So if this point has voltage V1, then this point also has voltage V1. So this is what we do in a forward bias. But let's say your diode is reverse bias. Then you simply open your circuit. So you simply open it. Means no current is flowing. No current can flow because it's an open circuit. So you opened it. Okay. So many people think that whenever the circuit is open, there is no potential difference. No, this is not true. Potential difference can be there, but current is not, because the circuit is not closed. I can apply the battery. Let's say I apply the battery, which is 3 volt. Then the potential difference here and there is 3 volt, but no current is flowing because the circuit is open. So whenever your diode is reverse biased, you simply have to replace your diode with the open-ended circuit. You open that circuit. You think that no current will flow in this diode. Okay. So this is how you solve it. With this information in mind, let's start solving the problems. So shall we start with? I have 5-6 problems and we can finish it up. I think we are exceeding the time, but anyway, we can do it. So we have 2 silicon diodes, and this is one of the PYQ, and they are connected to a battery, and 2 resistors are shown in the figure. So you can see one diode resistor, one diode this resistor, and you are applying the battery. Can you tell which diode is forward and which is not, which is reverse?
The top one should be forward.
Yeah, this is forward biased and this is reverse biased. And how will we replace? So it is given. You can clearly see the voltage drop across each diode is 0.7. It is given to you in the problem. So how do we replace it? So upper diode will be replaced by a battery and lower diode will be replaced by a open circuit. So this is now your circuit. So you can clearly see that what is the total voltage in your circuit? Is it 5.7 or 4.3? Are they adding up or are they subtracting up?
Okay, should be 4.3.
Subtract.
They are subtracting, right? Because this battery tries to give current in this direction, and this battery tries to give current in this direction. So both of them are opposing each other. Whenever positive of 2 batteries touch, they oppose each other. That is why the overall voltage in this circuit is 5 minus 0.7, which is 4.3 volt. And how the current will flow? Current will start from here, goes here. No current can go here because it is open. So current will go here, and it will come back to the same position as you started. Net voltage is 4.3. What is the net resistance in the circuit? You can clearly see only 10 ohm. So what will be the current in the circuit? Current in the circuit will be V by R. V is 4.3, R is 10. So total current in your circuit is 0.43 ampere. And this is
Excuse me, sir.
Yeah.
Okay, sir. Sir, I have a doubt, sir. In this diode, on this question, like on top of that, like, can you go to that diagram, sir? Like, the question one, sir.
Yeah.
Sir, like, if the current came from plus, sir, like from plus the current is coming. So while coming, it has two ways, right, sir? 2 ways, 2 possible ways. It will not take the right path because it is opposite bias, so it will go straight.
Yeah, it will go like this.
Yeah, it will take right.
Yeah, then it will take right.
Then it will come down.
Yeah, okay.
Now my question is, no, sir, not yet. Like my question is now again, it has 2 possible ways.
No, it does not have 2 possible.
Yes, sir. Why exactly, sir? Because now in current perspective, like it can.
This point is negative voltage, right?
Okay, sir.
Now this
So
is negative voltage. So
right.
this is positive,
Okay.
this is negative. So It is reverse bias on both the ends, right?
So the current won't take turn, it will still go straight.
Current will simply come. This is an open side. This is open. So if current has not entered, then current cannot come like this either. Okay.
Okay, sir.
Yeah.
Thank you, sir.
So finally, the current in the circuit comes out to be 4.3 ampere, and that will be the same current through your battery. So current through the battery is 4.3 ampere. Everyone clear with this problem? Please let me know, then we will move to the second problem. Okay. All fine, everyone? I explained you
Yes, sir.
all the details.
Yes, Bhaiya.
Yes.
Okay. Let's move to the second question. It's an interesting question. Difficult problem. The following Zener diode voltage regulator circuit is used to obtain 20 voltage regulated output at the load resistor. So they are basically saying at the load, your total voltage is 20 volt. Okay, fine. And there is 35 volt of initial voltage. Also fine. Zener diodes are rated at 5 volt and 10 volt. Okay, so this is little bit mistaken. It is 5 volt and 10 volt. So let's change. I have to change this problem because I misread the problem in the earlier. I read both of them as volt, but it is volt in one of them. Okay, let's do this. I will do this problem in front of you. Let me remove this, and I will do this problem in front of you, not a problem. And let's do. So both the diodes are at power of 5 volt. And the voltage, Zener voltage of both the diode is 10 volt. That is why you can see 10 plus 10 is giving you 20 voltage across the load resistor. Now, can anyone tell me the formula for power in a circuit?
VI voltage times current.
Voltage into current, right? So, what is the maximum current through the diode? The power is 5. Voltage is 10. So, how much current can flow through the diode?
Half.
Okay. So power, always remember, whenever the power rating is given, it means the maximum power your device can have. So power basically means if something is rated with some power, I rate this power as 2 volt, then the maximum power across this is 2. You cannot exceed that. Okay, otherwise your device will burn. So your power is 5 and power is voltage into current, and voltage also is given as 10. So the current through the diode is half.
Sir, can we get homework after all these problems? Like,
yeah, there will be.
Okay, sir.
Okay. So this current through the diode, whichever is coming, is what maximum current which can come is half. You cannot have more current than this. If you get more current than this, then you are in trouble. Your device will burn. Okay. So
Sir,
now they are asking.
Sir, like, why is their current going in reverse bias, sir? Like half
Current
ampere.
goes in reverse bias. Na? That is what we studied, right? In Zener, what happens? This current comes, right?
Oh, okay, sir.
We are now operating here, right? Zener
Okay,
diode is operating in this region. So we can have a huge amount of current, not just some current, but we can have huge amount of current. Okay. Okay. now Zener diodes are rated. So value of resistor. So we have to find this value of resistor. Okay. Can you tell me if the maximum current is flowing through the Zener, then what will be the current through the load? Okay. Or let me tell. So how much is the max? So if I want that all of my maximum current, I am finding the maximum limit. So if I'm finding my maximum limit, then I have to make sure that no current is flowing through load and almost all the current is flowing through Zener. That can be the maximum thing that can happen. In a circuit, what is the maximum thing that can happen? That current was coming up, and for some other reason, none of that goes to load, and all the current went to the Zener. So even if that happens, this current should never be more than half. That is what I want to achieve. So maximum current I can give in my circuit is half maximum. So I want to make sure that even if this happens, that my circuit can at max handle half ampere current. So the maximum current in my circuit is half ampere. So the maximum current in my Zener diode is half ampere. And that happens. The current through the Zener diode is maximum only when all the current is flowing through Zener and no current is flowing through load. So if you're trying to find the maximum limit, then what you have to make sure that current comes here, goes down, and like this. Nothing is flowing to IL. If nothing is flowing to IL, nothing is flowing to IL, and you know IZ, and if nothing is flowing to IL, then this IL, IZ, and this I will be same. So whatever current is flowing here, the same current will come down. So I will be equals to IZ, which will be equals to half ampere. Okay. So if this is the case, now can you tell me what is the voltage across this R? You can tell me that. What is the voltage across this R?
15.
15, because 35 is here, 20 goes here, so rest is 15. And current through here also we found as half. So voltage is 15, current is half. So what will be R? V by I, which is 30. So your value of this question is 30. So for safe side, you have to make sure that your resistor at least be 30 ohm. If it is not 30 ohm, then there is some chances that your diode will get burned. And in which case it can get burned? If all the current goes here and no goes here, and if your resistor is not 30 ohm, then it can get burned. So whenever you're finding the limit of resistor, there will be some questions which will be coming, and they will be asking that what is the value of resistor I should choose. In that case, you have to always ensure two things. Number one, all current going through Zener. So if you want to be sure, then you want to make sure that, okay, even if all the current goes to Zener, still my Zener diode should be secure. So first of all, whatever current is coming, you assume that all of them goes to Zener, just to be secure. Okay. Second thing that you assume is that if this is happening, then you do your calculations accordingly. So I assume that whatever current I was coming, that was IZ. So how I calculated my IZ? From the power rating. So I calculated my IZ from the power rating, and that came out to be half ampere. So whatever is the current through Zener, that will be the maximum current through the circuit. So the current through here is also half, and voltage through this is 15. So what will be the resistance? V by I. V is 15 and I is half, so it will be 30. So answer to this problem will be 30. Understood, everyone?
So will there be a case where the current will flow through the load resistance? Will there be a case?
Yeah. So if it flows, then your lower resistor will also work. So we are finding the maximum. Okay, this much resistor if I put, there is no chance my burning can happen. Okay. Obviously, in most of the cases, this is will happen. Current will come, it will also flow from Zener, it will also flow from load. But let's say I remove this load. Remove this load means I turned off my AC. I turned off my AC. So if I turned off my AC, it means I removed my load. So when, in that case, where will all the current go? In that case, entire current will go through the diode. So in that case, I have to make sure that my diode does not. Sir, can you tell that how we get 15 volt? Yes, I can tell you that. And that how we get is, I have 35 volt here and 20 volt here. So you can clearly see it is given in the question that 20 volt is across the diodes or across the load. So this is your 20 volt. So 35 is total, 20 goes here. So whatever is left goes here. So 35 minus 20 is 50. So the value of RL does not matter. In this question, it matters. It matters in actual, but we are going for secure purposes, that even if the RL becomes zero, even if the RL is zero and all the current is flowing through Zener, still we have to prevent our Zener from burning. That is what I'm trying to do.
Excuse me, sir.
Yeah.
So what are the cases when we are allowed to use this concept? Like in all of the question, we won't be doing this, right?
Yeah. This
like,
concept.
what are the series of questions where we're going to use this?
Where they're asking you series resistor. So series resistor is kept because of this purpose only. So why we put this series resistor? Anyone can ask this question. So the question for this series resistor is, first, to prevent the extra voltage. Second, to make sure that never this happens, that this thing get burned. Okay. So whenever they ask you the value of the series resistance, in that question you have to consider doing this. That if this resistor has to be chosen in such a way that this does not get burned. Okay. So whenever they ask you to find the values of series, because this is you have to decide. Load you can decide. I can put any load. I can put AC. I can put refrigerator, I can put mobile. In your circuit design, what you are in charge of is R, series resistor. Okay, you get my idea?
Yes, sir.
Okay. So this is entirely wrong. I misread the question. So this is wrong solution. Answer is 30. And this is correct. I remember answer is 30. Okay. Okay. Now last question. Next question is pretty easy. Next question says a diode at room temperature is given and the value of KT is given to you. It is 0.025 volt. And it says that it will have 1 microampere current when the voltage is 0.4. What will be the current when the voltage is 0.5? Then the current through the diode formula we already know. I equals to IS exponential EVF. VF is the voltage that we apply divided by KT minus 1. So I don't need to know IS because anyway that is not required in our problem and you will know why. What is the voltage I applied? So E remains as such. In the first case, voltage I applied was 0.4 volt. And what is the KT? KT is 0.025 EV minus 1. In this case, the current flows is 1 microampere, which means 10 raised to minus 6. And if you solve this up, this thing, very simple, E gets cancelled, V also gets cancelled. And this thing will come out to be 16. So this will be IS exponential 16 minus 1. Now they are asking that what will be the current if the voltage is 0.5. So again, I don't know the current. I equals to IS exponential. Again, E, then I put the voltage. KT value is already given. And if I do that, I will get IS exponential 20 minus 1. So this is exponential 15. This is exponential 19. So this is my equation 1. This is my equation 2. So if I divide equation 2 by equation 1, I will get I by 10 raised to minus 6. And this is exponential 19. And this is exponential 15. So your answer is exponential 4. And you have the calculator to solve that in the exam. So if you do that, your answer will come out to be 54.5. And if I bring this thing here, then your answer will be 54.5 micrometer. So your total answer to this problem will be 54.5. Yeah. Any trouble in this problem? VF
So
is the
what is the
voltage you
current?
apply. VF is the
So what
voltage
is
you
the
apply.
so current flow diode equation logarithmic circuit, sir?
What? Can you repeat?
For logarithmic, what is the formula through current diode equation, sir?
Logarithmic.
So one of the problem is given in CSIR net.
Can you send me the problem? I will see it. I will send you. If any additional problem is there, you can send it. Okay. Let's move to the one
Sir?
more problem. Yeah, please.
Sir, one small doubt, sir. Sir, this formula which you have told I is equal to IH current through diode, it was a constant current through diode. This formula was in the reverse bias condition, right?
No. Forward.
So
IS
forward.
is the saturation current.
Oh,
in
IS
that-
was. Okay, sir.
This is IS, but the current is in the forward.
Okay, sir. Okay.
Yeah. Okay.
Sir, this formula only works for forward, right? Or reverse as well?
In reverse, I have already given you the value that in reverse, this will be the current. That is
Yes,
not
sir, like,
changing with voltage.
my question is, what if we reverse the voltage? Like if we reverse the voltage and apply, will this work, sir?
Then you will actually see. No, it is only for VF. You have to apply here forward.
Okay, sir.
This you have to put here.
Only forward.
Yeah, you have to put forward voltage, positive voltage. If you apply negative voltage, then you will not get
Okay.
Okay. Consider the following circuit. Very important circuit question. And this is basically clipper clamper circuits. And I'm basically teaching you that if this kind of question comes, then you don't need to know that is it clipper clamper. You can just simply think that what is happening in the circuit. And let's see. So you have an input voltage and 2 volt is coming like this. So your voltage is sinusoidal. And you apply the voltage. And you have 2 diodes. And you need to see that what will be your VPQ, voltage across P and Q. Whenever such question comes, you have to divide your cycle into 2 parts. One positive cycle and another negative cycle. So let's see when I have the positive cycle. It means I am applying the positive voltage. So this is plus, this is minus. So I am applying the positive voltage. So this potential difference is positive. When if it is positive, then it is for sure, then this thing will always be reverse biased. D2 will always be reverse biased. So this will be open, so I can ignore this thing. So I can ignore D2. Only thing that matters now is D1. So now you can clearly see there are identical silicon diodes. For identical silicon diodes, I already told you the voltage is 0.7 volt for your potential pack. So now if your if your input voltage is more than 0.7 volt, this diode will get forward biased. And if your voltage is less than 0.7 volt, then this diode will not be forward biased. This will also be closed. Means no current will flow from here as well. So let's divide. So initially we are coming up with the positive cycle. So in positive cycle also we have two cases. One is that your voltage, so your voltage is less than 0.7. So if your voltage, input voltage is less than 0.7 volt, this was already reverse biased. So let's ignore it. Now, if the voltage is less than 0.7 volt, this will also be reverse biased. So no current will flow from here as well. So how your circuit will look like? This is your input, this is your resistor R, and this is like this. You can clearly see this is your open circuit. So no current will flow through it. No current is flowing. So whatever voltage is here, the same voltage will be here. Okay, it's just a battery. So when you have a battery, so voltage difference is there across the battery, but no current is flowing because the circuit is not closed. If the circuit is not closed, no current is flowing, but the voltage is still there. So between this point and this point, voltage is still there. So the voltage across VPQ will be same as your voltage across input. So your V load or VPQ will be same as V input. Okay, so this you can actually see. So in this diagram, if I try to show you that this will be my 0.7 volt. So unless I'm till 0.7 volt, my output and input will be same. So this will be my output. This and this will be same. So you can clearly see in these diagrams, you can clearly see that is why I'm getting these peaks, these lines. Because whenever my voltage is less than 0.7, my circuit is completely open. No current is flowing. So whatever is in the inner voltage, input voltage, that is the same as output. So in input voltage graph, if I show you 0.7 volt, this is my 0.7 volt. So whatever is my input here and here, that will be same as my output. So you can clearly see. So I will either get C, B, or D. Out of these three things, I can get any one.
Excuse me, sir. Sir, can you please repeat again? Like, why is it constant?
Why is it? Why is it?
Why did the graph go constant? Like,
no, graph
like,
is not constant. I'm coming. I am not explaining this part. I'm saying that till here, these two will come. I'm just explaining you these two. That till I'm lesser than 0.7, I'm less than 0.7. So my V output and V input is same. So this is my 0.7. So my V input is this and this. So my V output will also be this and this. Okay. Or it can be this graph or this, any graph. Okay. Now let's move to the voltage. I'm still in forward biasing now, but now my voltage is more than 0.7. So if my voltage is more than 0.7, this will get forward biased. And I told you the rule that if it gets forward biased, you have to replace it with the battery. And battery must have the voltage of 0.7. So this is now my new circuit. And can you all tell me that what will be the potential across PQ? It is clearly visible. 0.7 volt, which is a constant. I can give this in I any value. I can give as 3 volt, 5 volt, 6 volt, anything. But what will my voltage across PQ will remain? It will always remain as 0.7. So you can clearly see after a while, after you cross 0.7, then your voltage become constant. And then it will, and when you again reduce to 0.7, it will again come like this. So do you understand the forward biasing circuit?
excuse me, sir.
Yeah.
In the circuit below,
Yeah.
like below this, yes, sir. So like, if I increase the voltage like V, no matter how much I increase, the voltage through this diode will still be 0.7 volt.
Yeah, PQ voltage will still remain 0.
So the remaining voltage is the resistance eating it, sir.
So if I keep on So exactly. So if I keep on giving 10 volt, so or let's say 9.7 volt, so 0.7 goes here. So what will happen? 9 will go here. So if I make it 11.7, then 0.7 goes here, so 11 will go. So voltage across this will keep on increasing, which means current will keep on increasing. Current will keep on increasing, but there will be no increase in voltage across peak because it is same as the voltage of the battery. So after a while, what will happen? Your potential will become constant. This constant and this constant. So
Okay.
any three graphs are still possible. Now we have to see what will happen if I give the negative. Now if I give the negative voltage, negative cycle. So again,
Okay, excuse me, sir. Like I am just having a guess, sir.
uh,
So in when it gets reverse, D2 has some resistance. This means it will need more voltage.
It will need more, exactly.
This means it should be C.
Yeah, it should be exactly.
Okay.
Exactly. You are correct. So if I'm giving the negative voltage now you can easily predict that in order to make it reverse biased, sorry, forward biased again, in order to make it, so now what will happen if I apply the negative cycle, this is reverse biased. So this goes completely out of the picture. Now I have to look at this. So below 0.7, it is the same story. If it is below 0.7, then your circuit is open like this. You can clearly see your circuit is open. So whatever is the input voltage, that will be the output voltage. But now in order to make it forward biased, I have to apply more than 0.7 volt. I have to apply more than 0.7. Why? Because some of the voltage will also be dropped across this resistor. So let's say I'm applying 0.7. Then all of that 0.7 will not go to diode. Some of that will go to resistor. So effectively across the diode voltage will be less. So in order to give 0.7 volts to the diode, actually I have to apply more voltage. So if I apply, let's say 3 volt or let's say 1 volt, then only 0.7 voltage will go to diode and 0.3 will go to resistor. So now in order to make forward biasing, I have to apply the more voltage. So if I have to apply the more voltage, then my graph will become C. You understand this point, guys? Very important. This is how you read the circuits. Okay. So if I am applying, in order to make this diode forward bias, I should have 0.7 volt across this diode. But let's say I'm applying 1 volt here. Then only 0.7 will go here and 0.3 will go here. I cannot do like this. Like, okay, I am applying here 0.7 volt. Then all of it will not go here. Some will go here as well. So let's say 0.4 will go here and 0.3 will go here. So at 0.7 volt, I am not getting forward bias. Why? Because some of the voltage is also going to the resistor. So in order to make this forward biased, I have to have the negative of, let's say, negative minus 1.1 volt. Only then this will get. So I need more negative voltage than 0.7. So that is why your graph number C is correct. Yeah, guys. So what do you think? Yeah.
Sir, let's say D1 also has a resistance. So
Then upper end.
Then
it will depend which resistor is bigger.
Okay.
So
Sir, let's say both are equal.
Yeah.
Both are equal, sir.
Then upper and down will be same.
Okay. So the answer will be B.
Not D, B. Yeah, B.
B. B.
Okay. And this thing will not be 0.7. Okay. This thing will be something bigger number. Yeah. Okay, it will be B, and also this number will be bigger than 7. Yeah. Yeah, please.
Sir, when the voltage is less than 0.7 volt, then what will happen? Like, why the voltage is
so when the voltage is lesser than 0, let's say my voltage is minus 0.6, then this is also closed. No? This is not forward bias, no current is flowing through this, and this is anyway reverse bias, so no current is flowing through this. Then this is how my circuit will look like. Open circuit, no current. So whatever is input, that is the same output. So you can clearly see this is, so let's say this is my 0.7. So whatever is my input, this is my input, that will be your output. Okay. So input and output will be same in the case when both of them are open. No current is flowing through any of them. So whatever is input, same will be through the output. Okay. But once they get the forward biased, then what we will see is actually that so then this kind of thing will happen. Then we will have the battery here. Then what will be the output? Output will become constant, and that constant will be some fixed. Okay. Any doubt, anyone? Okay. Okay. So next two questions are pretty simple. It's on the same ideas we discussed so far. So let's try this question by yourself, and you can do it. And to all the students of my course, very humble request. Please attempt your PYQ questions of diodes. Okay. So there might be some few questions you might not be able to solve. So do them, discuss with me, send in the group, and we can discuss those questions. Okay, I can send you the solution of that or maybe something. And if some other formula is needed, I don't think that any other formula is needed. Rarely any question can come. Anytime any question can come, but more or less in diodes you need these formulas. Okay. So in the last class we did semiconductor physics. In this class we did diodes. Okay.
So,
Excuse
sir,
me, sir.
Yeah.
I have seen questions on Bose-Einstein condensation.
Yeah. Both lecture will come. Don't worry. I will take in time session. BEC will come. It will be, I will give you Bose temperature and all.